All right, everybody, welcome to another IAEI News Live. My name is Thomas Dimitrovich. Today is Tuesday. This is a recorded session. I'm in another meeting. And I apologize for not being able to go live or post the last 2 weeks. Life for me has been rough and very busy. So anyway, today I want to talk about and continue our discussion on motors. So let's talk and continue our discussion on motors, and it all starts now. All right. So as I was saying before, it's been a couple weeks since we've gone live. Last discussion that we had was on the last discussion we had was related to motors, and if you recall, we talked about in that we went through an example load motor. When I think of a motor, I think of a load. I mean, it's a load. It's a branch circuit feeding a motor. Now, you could have a motor, you can have a motor and some heaters, a motor and some control circuits. There can be more than just the motor on that branch circuit. Or I can have a feeder feeding multiple motors being served by a branch circuit. But regardless of the way I keep in my mind, and I think this helps me, I try to look at things in their most simplistic form. I was always taught in school to go back, even if there was if there's an equation, if you don't understand an equation, derive it. Go back to the fundamentals and work your way through to get to that equation. And then once you derive something, you have to understand it. So when I look at many things in the National Electrical Code or engineering and power systems design, I go back to the fundamentals. It keeps me grounded and it keeps it real. So when I look at the requirements in the code, when I think about power distribution and motors, I go back to fundamentals. It's a branch circuit feeding a load. I'm going to need to size the conductors for that load. I'm going to need to provide overcurrent protection for that load and the conductors. I'm going to possibly need to provide a disconnect. The load is going to have and draw current. It's going to have a voltage rating. So if I go back to the fundamentals, I'm pretty good. So last week, we went through those fundamentals. Now, or not last week, the last time we had the video, because last week I was at IEEE, the Institute of Electrical Electronics Engineers had a program or an event for the petrochem industry, put on by the petrochem industry. It's called IEEE PCIC. And there's a lady that I met there, and I've known Lorraine for quite some time. She knows motors very well, motor applications. She's got her own engineering firm, and she publishes and works on many different IEEE standards. She's out of Texas as well. So I saw Lorraine Padden. And Lorraine says, Tom, she goes, I was watching your videos. And she gave me some really good advice. Before I get to her advice, I made this statement a few times, I think, in our motor discussions. I look at motors like transformers. And if you think about the process I have for a transformer, when I'm dealing with a protection of a transformer, I get all the transformer details, and then I select the primary and secondary overcurrent protected devices, and then I select the primary and secondary conductors. That's sort of the order that I go in. Well, Lorraine's approach for motors and motor protection are very similar. And I want to review that with you because her insight on motors is very critical and could help. So let's talk about what Lorraine put together. Now, she does a lot of motor stuff. So she chairs a committee for IEEE who's developing standards and application guides for motors. And she told me about this article that she wrote. So apparently she was watching the program, and she goes, I just want to share with you one resource that you might want to consider looking at. And it was a magazine article and an IEEE document that she wrote. The title of it is called Simplifying Motor Coordination Studies. It's Lorraine Padden, PE. She has her own engineering firm, Padden Engineering, LLC, out of Katy, Texas. She's with Brown and Root, apparently, of Houston. And I see her at the PCIC. Her and I are going to do a tutorial on motor applications at the next either PCIC or Electrical Safety Workshop, not sure. But she explained her approach for a motor brain circuit. And it was very similar to my approach on transformers, where I focus on the transformer, get the transformer information, select the primary and secondary overcurrent protection, and then the conductors. Her approach, and she created a flow chart as part of this document. Her approach was to first get the motor characteristics. So the first thing you need is the full load. You look at the nameplate of the motor, or if you don't have the nameplate, say you're doing a design, you base it on the specifications of the motor. There are some assumptions you'll have to make just because you won't know the details. But she gets the motor full load current, the locked rotor current. You have to understand what the motor is driving, so you need the acceleration time. How long is it going to take to get from locked rotor to full load amps? You're basically drawing the start curve for a motor. And if you're not familiar with the start curve of a motor, I can share that with you. See if I can get this to work. Hey, and it works. All right, so if you think about the time current characteristic curve, let's draw. I need a thicker line than that. I went with the thinnest line. There we go. There. So if I think about the time current characteristic curve, let's move that up. This would be current, and this is time. And it's time in seconds. So what she would do is, she says she focuses on the motor and the motor characteristics. So she's looking at the asymmetrical, which is, let's do this in red. The asymmetrical start curve would look something like that down at close to 0.01 seconds. So this is 0.01 seconds. Then you'd have, that is your locked rotor amps. And then you'll know your full load amps. And then at some point, the locked rotor amps becomes the full load amps. And what you'll have is something like this, which is that transition from LRA to full load amps. So she basically establishes her start curve. She'll know her hot and cold stall times. She plots her symmetrical start curve, asymmetrical start curve. That's your asymmetrical. And then, after all of that, let's delete some of this. Since we know what these things are, then she will pick the overcurrent protection, your overload protection. Let's do that in blue. She'll pick your overload protection, right? And then after she picks her overload protection, she says she gets the motor service factor and or temperature rise, calculates the maximum overload device setting, and then if there's capacitors are connected on the load side of the overload, adjust the rating or setting. And she references a section in Article 460. Dadgummit. There we go. Yeah, Article 460. And then she goes, what is the type of overload protection? Is it a thermomagnetic breaker, meaning it's all as one? Because you could do this. Let's do a copy. Paste. You could say, instead of a separate overload, you could say, I'm going to get it all done. We'll make this one purple. We're going to get this done with a multi-case circuit breaker, right? So she says you have to know if it's a thermomag breaker, then she takes you down one path. If it's a dual element fuse, she takes you down another path. And if it's a bimetallic or static thermal overload, meaning it's separated from the short circuit protection, then she takes you down a third path. So I like the way, so she goes straight to overload protection and then short circuit protection. And then she selects either making sure that the molded case circuit breaker has the right rating, or if it's an so let's say that she did instantaneous trip only. Let's get rid of that. If she did an instantaneous trip only device, it might look something like this. Right? So this would be your instantaneous only in between, and the fact that you have an instantaneous only breaker and the overload, which is separate. Now you've provided both levels of protection. This is her process. Now remember, we haven't picked a conductor yet. So she goes straight to providing and selecting the overcurrent protective devices for this load. And then she selects the overload, and then she selects the short circuit, and sometimes overload and short circuit are all in the same device. And then she does a ground fault protection as well. And then finally she goes to the conductor ampacity calculation. And this is where she'll select her conductors. She'll apply her ambient temperature correction factors, her adjustment factors because of the number of current carrying conductors in a raceway. She picks the conductor size. Then she says, okay, if it's a 75 degree C terminal rating, then she'll say that you have to make sure that you protect that conductor at that 75 degrees C or 60 degrees C, depending upon the equipment, column, and she makes the statement that it may be necessary to increase the conductor size to meet these requirements. Without duration, and that's looking at the 75 or the 60 degree C column, making sure that your overload protection provides the protection of the conductor and the termination. And again, the termination more than likely is your weakest link. And that very much aligns with what we were doing before with ampacity. If you think about our ampacity discussion, remember our ampacity discussion was such that we said that if you have a conductor and a continuous load or a non-continuous load, you would pick a conductor size and an overcurrent protective device so that the overload, the circuit breaker or fuse rating, ampere rating, is less than or equal to the 75 degree C column if it's 75 degree C equipment. You can't go to the next larger. Well, they do the same thing on motors. The nice thing on motors is her flow chart is very detailed, and I think it needs to be updated for the sections for the latest editions of the code, which I just might do with her permission. And maybe we use this as part of our tutorial because we plan on doing a tutorial. We can base it on this process and pick different types of motor loads and walk through the process. And remember, if you have a variable frequency drive in there, then the drive primary is what you set for the overcurrent protection upstream. So motors can be complicated, but I think it's important that we don't overcomplicate, that we keep it simple and straightforward. Focus on what the load is, focus on if it's a single motor, if it's a multi-motor application, motor plus other loads, follow the rules for determining your current. Select your overcurrent protection, select your short circuit protection and ground fault protection. And then select your conductor. If you follow that process, I like that process for a lot of different reasons. I like the process of selecting your protection first and then sizing the conductor for the application. Because the driving factor for motor applications is going to be your inrush current, making sure that your overcurrent device does not trip. It's going to be your start curve, making sure your overload protection does not trip. And coordination. Obviously, ground fault protection too. So when you follow those rules, selecting those overcurrent protective devices first, narrowing in and solidifying the application with regard to these types of trip curves, and providing protection for the motor, letting the motor start, whether you have this type of curve, whether you have that type of curve or that type of curve or this type of curve, the slope of that curve to accommodate the starting of that motor, whether your knee for this motor is there, or maybe it transitions earlier, or maybe it transitions later, depending upon the load that it's driving. Understanding the motor start curve, understanding your overload protection and the function that it provides, understanding your short circuit protection and ground fault protection and the function that it provides first. And then you pick your conductor. That's your conductor damage curve. It's a process. I like the way she approaches motor circuit protection. It's very similar to the way I approach transformer protection. If we keep all of our ducks in a row, keep it simple, don't try to overcomplicate it. When things seem overcomplicated, break it down into parts. Understand that you've got to determine the load current. From that, you're going to pick an overload, you're going to pick a short circuit protection, you're going to pick your ground fault protection, and then finally you are going to pick and select your conductor that can serve the load based on its ampacity and that is protected based upon its termination. All of those pieces of the puzzle, once you put all of those together, I think it's worth it. I think it's worth trying to simplify things. Break the code down into its sections. If you look at Article 430, they give you a very good roadmap in 430.1 scope. They help identify the parts within Article 430 that apply to the various pieces of the branch circuit. Don't lose sight of that. Make sure you get your copy of NFPA Link so that you can bounce around the National Electrical Code and find those areas that apply easily and quickly. Because yeah, you're going to be in Article 430, but you can't forget about Chapter 1 and Chapter 2 and other areas of the National Electrical Code, Chapter 3. In Article 430, they talk about your adjustable speed drive applications. Make sure you get down pat and completely understand a single motor application. Then you can go to a multi-motor application and then get more complicated. I don't even say it's even more complicated. It's probably even simpler when you've got a drive involved. Know when and where you need to apply your disconnecting means. Don't forget about the fact that disconnecting means where required have to be lockable in the open position, and the lock has to be, the provisions for the lock to be, the provisions so that a lock can be placed have to be a part of the installation. That's in 110. So my message today, simple and direct. In motor applications, start with the motor. Work your way to overload protection, then to short circuit and ground fault protection, and then select your conductors. Let's keep that simple, and hopefully that helps you in your next application of motors. We'll see you next week. Take care, stay safe, and please stay healthy.